So, I mean, I've had this idea for a very long time, and you talked a lot with C about it, but I've had a lot of trouble explaining it previously, so maybe I'll have a better luck this time. So, here's here's the dream. Suppose we have some string theory, or M theory, or topological string on or times x, where x is some manifold of some dimension, and a brane of some kind, or times a point. So then from this, if we allow ourselves to dream, we can imagine building two algebras. With two associative algebras. One is AN, which is the operators on a stack of n branes. These are one-dimensional branes. B, which is the algebra of local operators of the gravitational theory on or across X. So this is an associative algebra by considering the operator product in this direction. In the or direction, makes B into an associative algebra. Okay. So then the dream or fantasy is that as n goes to infinity, AN becomes the Koszul dual of B. So, and I want to think of this as some version of holography. So, now, we can try to justify this in many ways. I mean, C and I have kind of thought a bit about how we could relate this to Witten's prescription for calculating the OPEs holographically. But I don't want to try to discuss this, try to give any theoretical justification right now. What I want to do today is just write down a very, very simple example and just go calculate everything and check that it works. Well, I'll check that it works maybe to leading order in the loop expansion, and then we'll kind of see some diagrams that we will have trouble computing to make it go further. And if you want a more complicated example, I have a paper on the archive as of yesterday doing a more complicated example. Okay, so the example I want to consider is a topological string theory. So people are familiar with the two kinds of topological string. There's an A model built from a symplectic manifold. And then the branes here are Lagrangians. And there's a B model built from Y, which is a Calabi-Yau manifold. And then the branes are coherent sheaves. But there's nothing, it's not normally considered, but there's nothing stopping us considering a mixture of these two things. We can have a mixed A-B model on X times Y, where the branes are, for example, products of L times Z, where L is Lagrangian and Z is a holomorphic submanifold. So this is from the abstract point of view in topological field theory, this is a perfectly reasonable thing to do. All we're doing is just tensoring these. We have a category of branes here, a category of branes here, and we're just tensoring them together to produce a new Calabi-Yau category. So the example we want to consider OR2, which is an A model, and C2, which is a B model. So the branes that live here will be some Lagrangian, well, that's not very interesting, it's just a line, times some sheaf on C2. Now, in order to be able to write down some algebras and see if this statement is true, we need to understand the open string theory, which is the theory on a brane, and the closed string theory, the closed string field theory, which is the kind of gravitational theory appearing here. So I'll explain what these are. So the first one, first I'll discuss the open strings. So abstractly, if C is a Calabi-Yau category, and I have some object, then we can construct a field theory whose fields are the endomorphisms. And the action comes from the A infinity structure. So this is some general abstract construction. How's it going to work here? And of course I should remark that this space is the space of open string states. So let's apply this general construction to a brane in here and see what we find. So
what are these the fields on? You said it was a field theory?
Well, it's a good point. If it was just a category, it would be a field theory on a point.
Okay.
But if my category was a sheaf on some manifold, then it would be field theory on that manifold, or on the support of that sheaf, this object. So as an example, suppose we take the brane OR times 0 inside of this guy. So we'd like to calculate the field theory living on this brane. We need to calculate the open string states. And the open string states are going to be, they're a tensor product of the A model states and the B model states. Okay, so what are the A model states? So that just doesn't care about that direction. So if you asked, consult the math literature, you find well the open string states to be the Floer cohomology of this guy. But that's really not very interesting. In this case, it's just the cohomology of OR. So we might think the open string state should be the cohomology of OR. But we want it to be a sheaf on OR, so we should model this by some complex, which is a sheaf. So we'll decide to model it by the de Rham complex. And if we take a point, C2b, the open string states this is the X algebra of a point. So that's, of course, since it's a point in C2, it's an exterior algebra on two generators. Okay. So, in sum, so the fields in the BD formalism of the open string field theory are.
Just a question, like with open string state, the first line referred to the B model, the A model, and the second line to the B model.
Yeah, and then we're going to tensor them together.
Okay.
Mm-hmm.
It's the tensor of these two.
Yeah, exactly.
Could you just maybe explain a little bit these two generators, what they represent?
So they represent motions in the normal direction.
So just the two holomorphic C directions.
Exactly, yeah. And yeah, they'll have a clear interpretation in a second as well. So forms an OR adjoin these two parameters, which are odd. Well, if I take n branes, I'll have a copy of GLN with a shift of 1. This is the fancy way of writing this guy. And if I have my field, we can read off by this procedure. I didn't write it down, but there's a standard procedure going back to Witten for figuring out what the action is. The integral over OR times, we do a Bayesian integral over C0/2. Okay. So this is what we find if we calculate the open string field theory.
And the shift of 1 on the GLN means it's a shift on the total thing, or it's just
That's right. So it means like the one form piece is in degrees goes to number 0.
So it's bosonic.
It's a gauge field. It's bosonic gauge field, right? And these two scalars are also in Gaussian number 0 because they represent actual scalars or the motions of the brain. So you want them to be Gaussian number 0. Yeah. So let me write that out explicitly. If we like D Battle and Bulkovskify it, we find a very simple quantum mechanical system in the non-BV setup. We find a quantum mechanical system the fields are A, which is a connection on OR, and two scalars. And the action is just a very simple action. Phi1, dA, Phi2, and then there's the usual gauge symmetry. So what I'm saying is that if you follow the procedure outlined by Alberto, you write down the ghosts and the antifields and the antifields to the ghosts and so on, you'll find the thing I wrote down in the blackboard over there.
Kevin, is there any way to see like how to, if you stack n brains from in the clubby out category, like is there any way to see the gauge group sort of showing?
Yeah, you take an object and you tensor it with c to the n, and I think it's endomorphisms. That means your tensor is endomorphisms with the endomorphisms of c to the n.
So this is some sort of AKZ where the source is some strange three-dimensional, right?
Oh,
It's not really three-dimensional, but it's something.
Oh, it's one-dimensional. It's AKSZ for
No,
the.
really, R is one-dimensional, but some sense is AKZ, some sort of Chern-Simons from R cross.
It is one-dimensional Chern-Simons, literally.
It's
Sure,
literally.
but you can think of R cross C02 something.
Oh, yeah,
three-dimensional,
that's right. And then it maps to BG.
Yes.
Well, and if you think about it like that, you'll see it's what you get from reduction of Chern-Simons on a two-torus.
Yes.
Where these two guys are the cohomology of two-torus. That's a good point of view. I mean, if you elaborate on that point of view, you will do some T-duality, you'll find you're back to the description Witten gave for Chern-Simons in terms of topological string theory. Okay, so what I'm going to want to do is like analyze the operators of this very simple quantum mechanical system when n goes to infinity. And I want to relate them to something coming from the closed string sector. So the closed string field theory will be built from the closed string states. And the closed string states will be a tensor product of a model, closed string states, tensored with the B model. So this, unfortunately, writing this down gets a little more involved and more homological, and I'm going to try to kind of minimize all these complications and simplify it. So the analysis we're doing here goes back to the paper of Bershatsky, Shikati, Uguri, and Vafa, who analyzed the closed string field theory for the B model on a Clavier threefold. And we're doing something very similar to that. So firstly, what is the A model? So the usual description would be if you have a symplectic manifold, the closed string A model should give you the cohomology of that manifold. Cohomology of OR2 is not very interesting. We want to have a field theory in OR2. So, of course, what we do is just, instead of taking cohomology, just take the de Rham complex. So for the B model, in the following BC of V, we should consider the subspace, the kernel of a certain operator inside the polyvector fields on C2. What polyvector fields? This is the Dolbeault complex of C2 adjoin two odd variables, del Z1 and del Z2. These are odd. So let's analyze what we get. I hope this is, yeah, sorry.
Is there any statement analogous to the open space statement, meaning if you take the Hochschild homology of F, of these atoms,
The Hochschild homology
kind of thing which can be used to construct?
Yes, I think the thing you want is the cyclic cohomology of that category.
And then you build an action.
Then you build an action by,
Is that good?
I mean, it's actually kind of tricky. What you should write down is like world sheets where you insert cyclic cohomology classes and integrate them. So for the 3.1 guy, you can calculate that by some cup product and cyclic cohomology together with a trace. But for the higher guys, it's a bit tricky. Although
we end up with like filler gravity thing.
well, so the point is for the A model, right? The A model is only interesting because of world sheet instantons. If you throw away the world sheet instantons, it's completely stupid. And that's what we're finding. There's no. I think you might find something like Taylor gravity in an appropriate gauge, but it's a really very stupid thing. It's just drawing complex.
It's actually, I guess I'm wondering if the Koszul duality statement about the string field theories can be related to the underlying Hodgson homology.
Yes, it can. It can be related to this theorem of Quillen, Lode, Segan, who tell us that the large N limit of the Lie algebra cochains is the cyclic homology. So that statement allows you to match that the single string states with the generators, with the single trace operators, the large N limit at the classical level. And the more interesting stuff is what happens when you do OPs.
So these OPs are essentially strings coupling attributes.
Yes. Mm-hmm. Yes. Mm-hmm. Okay, so let's analyze what this looks like. So what does it mean to be in the kernel of delta? So delta maps PVI star to PVI minus 1 star. So in PV0 star, this is inside the kernel of delta already.
This index is the polyvector field degree.
This is the polyvector field degree, yes. So PV1 star, things with one vector. Well, C2 is symplectic, so this is isomorphic to 1 star forms. And then the operator delta becomes the holomorphic de Rham operator delta. So we're considering the complex of closed, in the holomorphic sense, 1 forms. Now, if you read BCOV's paper, you'll get very annoyed at this point because it's never a good thing. You can't, in quantum field theory, you cannot say my field satisfies a differential equation. This is a big mess. And but they say this. And another thing they say is that the action functional is non-local, and the action functional is the inverse of del. So to write down their action, you need to use the inverse of del. So in this particular case, we can solve both of these problems at once by replacing this space by the image of del. So we replace.
In terms of polyvector fields, this del is just like a divergence operator.
Absolutely, yes. So these are divergence-free vector fields, or symplectic vector fields in this case. So replace the kernel of del, which is symplectic, by just del of omega 0 star, by omega 0 star, by its image under del. These are Hamiltonian vector fields. So I'm sorry to get. I don't want to. There's going to be a nice action functional once we make this procedure and things will work nicely. I hope it doesn't seem ad hoc. This replacement procedure doesn't really change the local operators because I've replaced this complex, the kernel of del, by something which is almost quasi-isomorphic to it. I've just added on. The difference between them is just the cohomology of C, which is trivial, almost trivial. So. Okay, so if we make this replacement, well, I should also say one more step. Well, also the kernel in the two polyvector fields. Well, the kernel of del here, that picks out things which are independent of z. So this is quasi-isomorphic to just C. The cohomology is C. So this is kind of trivial. This is pretty trivial. And also does not propagate. If you look at the definition of the propagator of BCOV theory, it does not involve these fields. They're really just background fields. So we'll ignore them. And it's really not.
Is this still like if I'm working sheafully?
Pardon?
Is this still okay if I'm working sheafully?
Well, this piece, the fact that it does not propagate, so what it really is, it's some background field, some deformation or symmetry. And this statement, if you work sheafully, is like, well, it's some topological field theory. We're coupling to some background topological field theory. And yeah. If we're going to consider operators, it would only consider like one additional generator, whereas the other guys, they have actual degrees of freedom and will contribute a huge thing. So this is not. So as I said, I hope this wasn't ad hoc. I just wanted to justify the final the form of the action we find as our candidate for the closed string field theory. So we have two fields, alpha, which is a form on R2 tensored with the Dolbeault complex of C2 with a shift of 1. So this is the one that's the Hamiltonian vector field. We have beta, which is in the same space, with a shift of 2. And I'll write the action over here. The action is the integral beta d bar alpha dz1 dz2 plus the integral beta del alpha. So it's a cubic thing. Notice del alpha, we can also write this thing as the integral of beta times a Poisson bracket of alpha with itself. So there's something about the Lie bracket on Hamiltonian vector fields included in the action functional.
So the base is what two-dimensional. We integrate over C3.
So, or two, it's 6 real dimensions.
Sorry, 6. Whereas previously it was.
So the quantum mechanical system lived on a line. So here's this whole 6 dimensions of spacetime. But
It has the double of the open string.
I wouldn't
The
say.
same was three-dimensional, was it?
Well, we started with this string theory in six dimensions. So this is the gravitational theory that fills the whole 6 dimensions.
This one.
This one, yeah.
Yeah. But the previous one was
The previous one was that the theory just on the brain, so it's just on the dimensions of the brain, which is 1 dimension.
Okay.
So to maybe hope people can understand this action a little better, let me dBVify it, and it'll become something pretty simple and hopefully familiar. It's very closely related to the BF theory, the 4 dimensions that Alberto was writing. So if we're on OR2 cross C2, take the coordinates here, call them xi, coordinates here are zi. Beta has components beta x1, x2, dx1, dx2. This is like the Gauss number 0 components. plus beta z1, z2, dz bar 1, dz bar 2. And alpha has components. It's a 1. And then we just have this action. The action is as above. So beta has some one-form gauge symmetry. Alpha has zero form. And this, just like in the BF theory that Alberto mentioned, this one-form gauge symmetry has secondary gauge symmetry, which is why we get this big complex. Okay, so let's see what's the meaning of this. So these terms, since alpha is a Hamiltonian vector field, this thing here, this is a Beltrami differential. Where we deform C2 as a symplectic surface. What are these terms? So again, alpha is a Hamiltonian vector field on C2. So this is like a connection on R2 valued in Hamiltonian vector fields. So these terms say we're making a bundle of C2s over R2. Flat bundle of C2s over R2. Okay.
I assume the flatness is in the equations.
Yes, the equation, exactly. Yes, I should have said that. And the fact that this is an integrable deformation of complex structure is also the equations of motion. So in sum, for example, if we put this on, to understand the phase space, for example, like Alberto was saying, or times S1 times X, where X is holomorphic symplectic, then the phase space is the cotangent bundle of the moduli of holomorphic symplectic surfaces fibered over S1 plus a flat connection. Okay. So we've sort of derived this, but okay, any questions? Okay. So once we write something like this, I hope it's kind of plausible that this is kind of gravitational. Like the phase space is the moduli of some geometric structures. Some moduli. Yeah.
Just like the, sorry.
Yeah.
I was just going to ask, is there some analogous description for the meaning of the betas? Did you say? Sorry, maybe I missed it.
These are, if you look at the action, they only appear linearly. So they're really just Lagrange multiplier fields enforcing the equations that we have an integrable deformation of complex structure and that this connection is flat. So just like in BF theory, B is a Lagrange multiplier ensuring F is 0.
That's why it's a cotangent bundle, isn't it?
Exactly.
Sorry, I missed some in the last sentence. You put this on something that depended on X, and then you got something that.
Well,
do you mean like it's the cotangent space at X or something? Like
well, if we worked in perturbation theory near X, we would find this moduli space near this configuration.
Okay.
It doesn't really, because it's a gravitational theory, it doesn't really mean to say, when I say putting it on X, that's like with the theory with the connection saying putting it on a manifold near that connection. Okay, so I hope we've now we've set up our two theories. We'd like to compute our algorithms of operators and check that they're causal. This is our task. Oh, there's one more nice thing. So if I give you a closed string field, that should give me a deformation of the gauge theory on the brain. So for example, if my brain is on the line x1, and my closed string field is like dx1, z1 to the k, z2 to the l, you can think, well, this gives some deformation for a quantum mechanical system. What deformation is it? It means we deform the action, which we wrote down earlier, we add on a Hamiltonian. Okay. So that very many matrix models with Hamiltonians can be engineered by these backgrounds. And it's clear why this has to be true, because this just means our C2 has a connection which moves some parallel transport. So, okay. Okay, so let's do some computations. What are the operators in the gauge theory? So fortunately, we had Brian's talk earlier, and Brian explained that in these theories where we find the de Rham complex, all the local operators cannot have any derivatives in x. Anything involving an x derivative can be killed by the BRST operator. So we're only going to care about things which involve just values of these fields at a point, but also of the antifields and so on. So the Gauss number 0 operators, the only thing we can do, these are generated by things like the trace of some polynomial, where this is now a non-commutative polynomial in these variables. These are all we're using is, classical 19th century results on invariant theory. The algebra of invariant things in two matrices all look like this. And as n goes to infinity, there are no relations. So at finite n, you might have some accidental relations among traces of matrices, but they don't happen at large n. So Gauss number -1, we'll have things like the trace where psi is equal to the antifield to the connection. And as you go up, there'll be more stuff. But it turns out essentially by using the load equivalence secant theorem, or just by doing it by hand, you can compute exactly the cohomology of the BRST operator. So the most important thing we're going to need is that because in the action, the cubic term looks like this, phi1, A, phi2, and we can rearrange this to be trace A, phi1, phi2. So by cyclic symmetry of the trace, if you think about what does the BRST operator do to the antifield of the connection, it turns it, because it appears at phi1, phi2, it turns it into the commutator. So Q of trace psi so as a corollary, in Q cohomology, these expressions involving traces of non-commutative words in phi1 and phi2, we can just commute the phi's past each other at the level of cohomology. So that a basis of ghost number 0 operators is trace phi1 to the k, phi2 to the l. Okay, this is going to be, when we analyze the string theory or the gravity theory, well, this will correspond to these polynomials, z1 to the k, z2 to the l. So we kind of see them appearing. Now, similarly, there's ghost number -1 operators, a basis, if you compute it, well, trace psi, phi1, phi. I hope you'll allow me to write this. The notation is slightly misleading. To get something actually in the kernel of the BRST operator, this expression has to be made totally symmetric. But the basis looks like this, plus permutations, which I'm not going to write.
So I should think this is like a PBW basis for some algebra that you're going to tell us to do?
Yes. Yeah, we're going to put, but I'm only going to commute a little piece of the algebra. So therefore the classical local operators are the symmetric algebra, polynomials in two variables, plus another copy of it. Great. And if you think about it, you can kind of see exactly the two fields of the gravity theory, alpha and beta, emerging. And there are no other local operators. Okay, so let's figure out what the local operators of the gravity theory are. So I won't give all the details of the analysis, but by using arguments kind of similar to what Brian said, for example, think like what kind of local operators can we build? We can evaluate beta and alpha at a point. We can differentiate them. But by a cohomological argument, only the zero form parts of alpha and beta will give you actual physical local operators in the Q cohomology, and only the Z1 and Z2 derivatives can contribute because the other derivatives can be cancelled by a Q of something. So the ring of local operators is generated by by the operators which send alpha to del z1 del z2 to the L alpha. This is of ghost number 1. This is of ghost number 2. Notice these operators have kind of the opposite transformation properties as these ones.
Mean data.
Pardon?
Mean data.
Yeah, sorry, thank you. So if we write it out more carefully, we find that the ring of classical local operators is Chevalier cochains of polynomials in 2 variables So these polynomials in 2 variables, this is the alpha field, solution to the equations of motion. And this is a Lie algebra with the Poisson bracket. And this guy is just acted on it, it's the adjoint module. And I take it with a shift of 1. So this guy is the alpha, this is the beta. Okay, any questions about this analysis, or is this?
Where is the Lie bracket of Z1 and Z2?
What is the Lie bracket?
Yeah.
Oh, this if I take a guy here, I'll call it alpha. Beta. Alpha of beta is the Poisson bracket of alpha acting on beta.
The Poisson bracket is just dz1, dz2, like Z1 and Z2.
Yeah, exactly. The constant Poisson tensor, yeah. So like these are Hamiltonian.
It's like a non-commutative plane.
It's not quite non-commutative. It's like a little bit. But you can also think of.
Because alpha, beta, okay.
And these are like Hamiltonian vector fields. These are functions with the natural action of Hamiltonian vector fields. Okay. So now.
But alpha with alpha commute and beta with beta commute.
No, alpha with alpha is also the Poisson bracket.
Okay. And beta with beta is.
Beta with beta commutes. Okay, so I think we have some kind of experimental verification of the proposal because, well, if we take the Koszul joule of this, we find something that looks almost exactly like this. And the almost can be fixed by thinking carefully about various parameters. So the Koszul duality takes Chevalier cochains into a universe enveloping algebra. Ultimately called Hamiltonian vector fields in C2 plus adjoint representation. And you compare this to and we see that they are the same, except that this guy is really the classical limit of this. So commutative limit. So let's write out carefully what we've discovered. The commutative, so think, look, what's the meaning in terms of gravity of taking this commutative limit? Well, it's commutative if we throw away the interaction, because the interaction is what generated the Lie bracket. So the commutative limit is the operators of classical free gravity theory. So we find that classical free gravity is turns by causal duality into the classical gauge theory. Okay. Any questions so far? So maybe the next step would be to say, how would I move away? How would I recover this actual universal enveloping algebra? Or what do I need to do? Of course, what you need to do is move away, like to see the first order correction away from the symmetric algebra. You need to move to first order away from the classical limit.
Here, are you suggesting that the coupling constant on one side is the h bar on the other side, or what's the correspondence you're
Right.
you're trying to prove at first order?
Right. So if we take this theory in the planar limit, then the coupling constant, which kind of measures the loop number of the diagram, is going to be, take in the planar limit, then the h bar over here will be the interaction strength over here, which you see, for example, this thing is maybe a two-loop diagram from the gauge theory, but is a string theory interaction. You see this kind of pattern, which is why.
And then what would be the quantum gravity? So the h bar on the gravity side.
So that's going to be the beyond the planar limit. So to figure out what h bar is on the gravity side, you have to think a bit about how many traces are my operators. And you include a parameter in my OPE by saying I take two single trace operators. This gives a spectrum of various operators of various traces, and I have a parameter there. That'll be related to the computational coupling constant.
It's like the power in
Yes, it's like that, but not exactly the same.
So I don't think I know what free gravity is and how it's different from what you.
I just threw away the interaction. I said it is. I just have a quadratic thing. Okay, so let's do the first order correction. So we see that this guy corresponds to this operator. So we want that the Poisson bracket should be the first order non-trivial quantum correction. So this is the order h bar term. But if you're keeping up and you know how to do these calculations, this is like obviously true. All we do is here's some trace of products of the phi's. To complete the first order correction, I link them by diagram. So it's going to be the sum over all ways of connecting one of these guys with one of these guys, and that is the Poisson bracket. Okay. So it matches to the free limit, it matches the first order correction away from there, it matches. Let's see if we can get our hands on any more complicated diagrams and see if we can match up the computations. So unfortunately, it turns out if you try to do this in this particular example, we rapidly come into computations that I don't know how, kind of gravity's computations that I found too hard. But there are other examples where I've done it and it works. So suppose we work to order h bar squared. Well, it turns out for symmetry reasons, this commutator, I mean, this algebra has it's an even quantization, which means if I send h bar to minus h bar and reverse the order of the product, I get the same thing. So to order h bar squared, there's no commutator. There's no corrections. So let's work to order h bar cubed. So we can write down some corrections that appear on the gauge theory side. How do they look like? Well, I'll write down my local operators, some traces of the phi's. For simplicity, we're just considering ghost number 0 operators. And to be order h bar cubed, they should have 3 edges, like that. There's this kind of thing, and there's also this kind of thing. They're ribbon graphs because we're in the large n limit. Okay, so this first one, A is a correction where I take the commutator of trace of something is equal to a cubic expression in traces. B is an expression where the trace is equal to a quadratic expression. So let's see if we can try to match these up on the gravity side. Does this make sense? So it's cubic because how many boundaries? 1, 2, 3. 1, 2.
So I'm a little bit lost.
Sorry.
It's okay. So in the B diagram, that's not a genus 0 diagram. So you're picking up some order in the
Yes.
in N as well. Or I'm confused about how h bar and capital N are related.
I really don't want to go into that. I want to be more naive and say that picture looks like this picture,
Okay.
and I'm going to draw the other picture in a second. I mean, this is a torus with 2 punctures, and I'll write down a 1-loop diagram. Okay, so how will we compute this? Maybe. How would we compute this in the gravity side? Let's see. Well, the thing we know, we have the algebra of operators on the gravity side, this cochain algebra. We might know how to compute the A-infinity structure there. And the cochains of well, we might write down diagrams if if I have operators say O, K, L, maybe del Z, K, del Z, L alpha to compute the infinity structure.
Just for people who are not specialists of A infinity, I mean, A infinity, can I just think as some kind of deformation of that? Is that so? Is there a way to think it as a real deformation of your complex or algebra?
Yeah. Well, I mean, once I think the diagrammatics are pretty straightforward for what it means. It's just inserting some operators and doing some kind of integrals. But maybe the thing to say is, if you look at these guys, here I have 2 traces and I spit out 3 traces. The way Koszul duality works is that this gets switched around. So this will be an operator which takes 3 generators and gives you 2 generators. So this will be a M3 A infinity operation. And this guy is 2 generators to 2 generators, so this will be the usual product in the algebra.
And also, like, the source is anti-commutative, and in the product it becomes commutative. Is that
Yes, because here it's like, exactly, and that's why you have an exterior algebra and symmetric algebra. So the Poisson bracket between an exterior algebra should be symmetric, which is why this is symmetric. Maybe I won't go into the details about the infinity, how to compute it. I'll just write down the kind of diagrams you do to compute it and how it will match. So to compute the M3, the first non-trivial one, well, I draw a line, and I put 3 local operators. One is at 0, one is at epsilon, and one is at some point t. And I put 3 operators. And I just draw the Feynman diagram. I draw all possible Feynman diagrams in this order that can connect them. And the A infinity structure is computed by drawing this configuration, and you do the integral from t equals 0 to epsilon, and then the limit as epsilon goes to 0. So it's a very reasonable physical configuration. The thing here is a certain descendant if you're an expert. So this gives you a 3 to 2 A infinity operation. Because I have 3 operators, and I spit out something which is quadratic because of these 2 external lines. And this is supposed to correspond to the 2 to 3 on the Koszul dual side. So in principle, you could sit down and write down your integrals and compute this, and it should match the coefficient you find there. It's a kind of very concrete thing. I haven't done this one. I've done a related one. For M2, the first non-trivial M2 that appears, so I put one operator at 0, one at epsilon, and to get something with a non-trivial answer, I have to have a loop diagram. This is one loop. Then I take the limit as epsilon goes to 0, and I find what I get. And this corresponds to the 2 to 2, which was this one. Okay. So if this conjecture is true, it really says you can go and calculate things, the infinity structure using diagrams, and the diagrams you find are exactly the same shape as these ones. And the coefficients should match up. Okay, but this is super hard. Like, even though this is a tree, like, computing this integral is like crazy hard. Okay, so I'll stop there. Yeah.
After one does these hard calculations, is still is there any trouble in comparing to A infinity? Could there be A infinity isomorphisms to worry about?
Oh, I mean, I think that the best you could hope for is, say, like, they are isomorphic. It might not. Maybe you could do some algebraic computation to say the A infinity constraints fix it uniquely. In practice, the only way you could do this would be, first, you do some algebra and say there is only one deformation. Then you compute one diagram that fixes it.
Yes.
Because if you have to compute this diagram, I mean, I wouldn't want to, I don't know.
Have you computed any of this diagram?
Yeah, so the one I've computed is, it was a slightly more complicated setup, because there was an additional brain, which was like a background brain. And this is an additional 5-dimensional brain. And then in that one, there's a diagram which looks like this. And I've computed that one. I was doing this work with like Witten and Yamazaki about the Yangian, and we were trying to do similar kind of Koszul dual things. And then we tried to, we tried to compute this diagram. So this diagram will give you a certain relation where 2 generators of the Yangian become a cubic expression. But we had a really hard time fixing the factors, and we couldn't. Then we were off by 4 or something. It's really nasty. I don't know. Yeah.
Well, at some point you throw away some kind of zero mode in the gravity sector. Is there a place where you think it might come back and help, or it's just completely?
Oh yeah, no. So the way this works is, so on the gauge theory side, there's a choice you make. Do I treat GLN as a Lie algebra? If I treat it as a Lie algebra, then I can have functions of ghosts. But I could also treat it as a reductive group. And if I treat it as a reductive group, taking GLN invariance is an exact functor, so I shouldn't involve ghosts. I shouldn't take Shivali cochains. So this choice of how to treat GLN is exactly reflected in the choice of what you do with these descendant fields, these outer fields. So like we're missing a bunch of. If we included all the cyclic cohomology, we would have a bunch of kind of topological stuff in our gravity field theory. These would exactly match with the invariant polynomials of the ghosts. There's like trace of x cubed, trace of x to the 5th, and they all match.
So you told us a story where the gravity side was just something of closed string state. It doesn't require choosing a brain. On the gauge side, you decided that the brain you were going to pick was like a point times the Lagrangian. If I choose some other kind of B brain, what what happens?
So then you have to think about them. Then you don't have an associative algebra anymore. You have, some exactly, or some factorization algebra. So you have to say it's Koszul dual in that world. So the simplest thing to say was, suppose we had more topological directions and we had a 2-dimensional topological theory, then I would have an E2 algebra, and you're going to say that E2 algebra is E2 Koszul dual to the gravity thing.
So how do I tell the gravity theory that I want to study its E1 Koszul dual?
I mean, the gravity theory is some, En times some holomorphic thing, and you can just decide, I'm going to take Koszul dual in these directions and not those ones.
Here was important to scale the out. So could you go to actual times C5 or can we?
Yeah, or 3 times C4. C4, yes. You could totally study D0 brains, and that would be D0 brains, and there would be some complicated thing, and yeah.
So this would be some complicated calculation in these order quantum mechanics.
Yes.
Semi-protected.
Exactly. Yeah, of course one could fantasize you could see M theory from this. But
Here you see.
If there are no more questions, so before we thank Kevin again, so we'll have this kind of discussion time at 2, and this is totally flexible what we talk about, but so some possibilities are that we could sort of, it would be exciting to expand on the very end of yesterday's story from Phil, Dylan, and probably Brian on the mode relations to WCW and sort of these final results that were only mentioned. So that's one thing that would be exciting to discuss. The other is probably like different ways that Koszul duality appears in field theory. So those are some possibilities. So, and let's thank Kevin again.